Welcome to our final unit in Physics 12. So that topic is electromagnetism. So in the last two topics, we were looking at circuits and electrons and current. For this one, what we discover, or what we'll see, is that current and electrons results in magnetic fields, and magnetic fields can create current. So they're interconnected, these two concepts. Now, calculations in this are quite simple, but what makes this topic challenging is more so really understanding what is going on. So we'll start with this day one stuff, with just making sure we understand what a magnetic field is. So here's our first one. Let's imagine we have like a bar magnet. We've all seen this before. We know that if you put two north magnets together, they're going to repel. If you do a north and a south, they're going to attract. But just like in electrostatics, well, in electrostatics we saw that if we have a positive charge and a negative charge, we can draw these field lines that show the direction a positive charge will travel if placed in the vicinity of these charges. And we always drew those lines from positive to negative. We draw from positive to negative, positive to negative. So for a magnet, we can also draw magnetic field lines. So if you have a north and south pole, we always draw an arrow from the north to south. So for example, something like this. So we have magnetic field lines. Again, they show the direction of our magnetic field. It's going to loop around. So for magnetic field lines, we always draw from north to south. And if we draw it properly, we can see, like, if you look at the density of the field lines, we have a stronger magnetic field when the lines are closer together, and a weaker magnetic field when they're further apart. If we have two bar magnets like the following, then we could draw the arrows from north to south, so we're going to have magnetic field lines drawn like so, and from here it's going to go to the south pole, and north to south, north to south. Just showing a rough example of our magnetic field lines. Okay, so north to south, north to south. So something like the following. Okay, let's scroll down. Here's a couple more examples of that. And you might want to try to if you want, you can pause it and give it a try yourself. If not, just continue along. So in this one because we have two north ends next to each other, we know that they're going to repel. So these arrows are being repelled from each other. So north to south, north to south, north to south. Some of you may have played with those metal filings that you can place around the magnets. If you've seen that before, and if you put a magnet and those metal filings around it, and you shook the plate, you see them all kind of follow this path. You'd see the general direction of the field. Again, it's not going to show you, the metal filings aren't going to show you, are you pointing north to south to north, but you can see the general path. How a compass works is the arrow is going to point along the direction of the magnetic field. So if I placed a compass right over here, the compass arrow is going to point in this direction. Put a compass over here, the compass arrow is going to point in this direction. Compass arrow is going to point in the direction of the magnetic field line. Again, the second one's going to look exactly the same as the one above, but our arrows are going to be reversed, because instead of the two norths next to each other, it's the two souths. And so on. Okay. Scroll down some more. Now we're going to start looking at what happens when there is current. So what scientists discovered is that if you have current flowing in a wire, it produces a magnetic field. And we use what's called the right-hand rule. I'll have a picture in the next video. But generally what happens is if here we have this wire right here, here's our wire right there. And this is when you're talking about conventional current, we use our right hand. If you're using electron flow, you want to use your left hand. So if you're following what we used in the previous lessons, we always worked with conventional current, so the flow of positive charges. Okay, so we're going to use what's called the right hand rule. So if you take your hand and were to place it around, if you maybe just grab a pen, like a pen or pencil in your hand, you wrap your hand around it. So if I were to wrap my hand around this wire with my thumb pointing in the direction of the current, so let's just kind of draw in that thumb. So there's my thumb, and my fingers are going to wrap around it. Look at that art skills right there. Yeah. Okay. So my hand wrapped around it. Got my fingernails right there. If I do that, what this shows me is it's how you remember what direction the magnetic field will result in. So I place my hand, my right hand, for conventional current. We can see that the current's going up, denoted by my thumb, and my fingers tell me the direction that the magnetic field will travel in. So if I can draw like the following, it's going around in this direction. So behind and around and over on the side. So that's the direction of the magnetic field that will result around this wire. Again, it works the same if I'm using electron flow. So if I know a conventional current is up, that means that the actual flow of current, the electrons are traveling downwards. So this is electron flow. Electron flow. So if we're using electron flow, we have to use our left hand. So what we can see is that my left hand thumb would point down. There's my thumb. And my fingers would, as a result, wrap around. Wrap around. It's kind of harder to show, but you can see it's going over top of these. Over top. What it shows, though, it still shows that the magnetic field is still in that same direction around the wire. So again, it doesn't matter if you're using electron flow or conventional current. Electron flow, use your left hand. Conventional current, use your right hand. Still will get you the exact same result. This next one is called a solenoid. So if you were to actually look at just a single tiny wire, so we can see, let's just look at like this segment of wire right there. We're looking at that segment of wire right there. If we use that same row, we can say, okay, that current is going up and around. So if we're looking at just this wire, if we were to wrap our right hand around that part of wire, we would see that it creates a loop like this. Our fingers create a loop in this direction. Same over here, it's going to create a loop in this direction around this one. If we looked at like one of these ones, the current's going up, and it's going to create a loop like that. What it's showing, though, is like in the down the middle, we can see that it's creating a magnetic field through the center of the coil. So what happens is solenoid kind of acts like a magnet. So with the current flowing in this direction, it results in a magnetic field that goes through the coil in this direction. This end ends up acting like a north pole. This end acts like a south pole, and we get magnetic field lines that go around the solenoid and through. So around and through the solenoid, around and through the solenoid. Okay. So instead of having to look at each individual wire, the easier way to do it is imagine the wires that those are going to be your fingers. So if you were to place your whole hand on this thing, let's see if I can draw it. My thumb would be pointing in this direction, and my fingers look like the following. Here's my palm right there. Okay. You can see if my fingers are in the direction of the current, my thumb points in the direction of the magnetic field. So you can see the magnetic field is going through and around, through and around.